Welcome. Today we'll review some multivariable calculus and try to connect some of those ideas to machine learning. So for a simple machine learning example, imagine that you have some points which are stored in a matrix A, and you want to come up with a line that approximates the set of points as well as possible, in the sense that the sum of the squared vertical distances from the line to the points is as small as possible. One way to formalize this is to define this function, capital L, which we call the loss function, which keeps track of the sum of squared distances. So this is the function that we're trying to minimize when we choose our parameters m and b. This is a really simple example, and it's possible to solve this problem with linear algebra and not use calculus at all. However, this pattern is something that is riffed on very frequently in machine learning, where we tweak our loss function in various ways. We come up with a different class of functions that we're trying to use to approximate our data. But the basic structure of having some loss function and trying to minimize it is very common. And in general situations, we're going to have to think about that in calculus terms, because the loss function won't necessarily be as simple as this one. So the main optimization theorem for a multivariable calculus, this theorem really sort of combines a few different ideas from a multivariable calculus class. But essentially, the point is that if you have a differentiable function that has the local extremum at a point, then a point where the extremum is inside the domain and the gradient is 0. And the reason the gradient can't be 0 for a point inside the domain at a minimum or maximum is that if the gradient were non-zero, it would be telling us that locally around that point, the graph of the function is tilted one way or the other. So there's going to be directions you could go to increase the function, opposite directions in which you could decrease the function, and it can't be a local minimum there. So inside, the gradient has to be 0. On the boundary, it's not quite as simple, because it could be that the graph of the function is tilted there, but in order to go up, you would have to go directly away from the domain, which you're not allowed to do. So the proper generalization of that is the Lagrange equation, gradient f equals lambda gradient g, where g is some function such that the boundary of the domain there is a level set of the function g. Alternatively, if there's a corner in the domain, that also has to be checked separately. That could be a local min or a local max, regardless of the Lagrange equation or the gradient equals 0 equation. Okay, so in this first problem, we're going to actually find the line of best fit above using some calculus. But instead of doing the calculus by hand, we're going to get SymPy to do it for us. And SymPy is a Python library for doing symbolic mathematics. And this package, sympy.jl, is a Julia package that wraps that one. The instructions here tell us what to do. We define our expression L in terms of m and b. So this macro vars is declaring m and b to be variables in the algebra sense within the package SymPy. So we can then combine them using algebra rules and store the new expression we come up with as L. And we're asked to find the critical points, assuming that there's no restriction on m and b. So the only possible critical points are going to have the gradient equal to 0, and so we differentiate with respect to m, and we also differentiate with respect to b, and we want to set both of those equal to 0. And the sympy.solve function, just to simplify our lives a little bit, it requires us to just put the left-hand side, and the right-hand side of 0 is assumed. And then we put the variables that we want to solve for here, and we just run this line of code, and we get a dictionary back which tells us the variable m should be 33 over 49, and the variable b should be a7 over 49 if the point m comma b is a critical point. And since there's only one solution here, we can tell that that's probably going to be the unique minimum. Just from the original problem, it's easy to convince yourself there should be one line that kind of cuts through here and does as well as possible, and if you move away from that line, it gets worse. If you move it up or down or tilt it, it's not going to fit the points as well. So let's take a look at that. I've used this Plotly.js, it's called a backend for the plots function, because I want to be able to manipulate the graph. But we declare our ranges for m and b, and then we plot L as a function of m and b. So we're just looking at how bad. So the z-axis here, the values on the z-axis are indicating how bad the fit is for a particular M and B combination. So, and I've plotted here the point 33 over 49 and 87 over 49, which is the place where there's a minimum. And what you can see is that this loss function has a very valley-like shape. In fact, if you look straight down the line here, it almost looks like there's not a single minimum, but in fact a whole line of minima that run along the bottom of this valley. But clearly, as you move the slope far away from the correct value, the loss gets large very quickly. But actually, it does curve upwards in all directions here, and we can see that by changing the z-limit to something much smaller, like 40. So we're kind of zooming in around the point where the minimum is. And what you'll be able to see is that there's some curvature in the more shallow direction as well. So we had to look at a more narrow range of z-values to see that, but the orange point clearly is at the minimum of this loss surface. Okay, so let's put an extra wrinkle in. The values that we found above have the property that if you square sum them, you get a result bigger than 3. And someone might ask you to find an m and a b value that minimize the loss function subject to the constraint that m squared plus b squared is less than or equal to 3. And we'll see next class an example where we do want to put a constraint like that and it has some practical benefit. So the trick here is to solve the Lagrange equation. We have a constraint now, and intuitively we don't really want to look for values where m squared plus b squared is less than 3, because ideally m squared plus b squared is going to be equal to something larger than 3, and we're having to make some sacrifices to get m squared plus b squared down to 3, and we probably don't want to have to give up any more than we need to. You could consider the interior of this circle separately, but we're just going to look right at the circle so we can jump straight to Lagrange's equation. So we'll begin by declaring m and b and lambda to be variables, and we'll let g be the constraint function, which is m squared plus b squared. You could also do m squared plus b squared minus 3. That would be just as good. And we're just going to follow the instructions. So we're asked to use nsolve instead of solve, so it'll use a numerical solver. And the equation we want to solve is that the derivative of L with respect to B, so the derivative of the objective function, is equal to lambda times the derivative of the constraint function. So that's true in the B coordinate, but we also need that equation to hold with respect to the m coordinate as well. And now we have 3 variables, m, b, and lambda, in 2 equations. So we need another equation if we expect there to be a unique solution. And we remember that in fact g needs to be equal to 3. So we do g minus 3 there. And we're going to be solving with respect to m, b, and lambda. And the problem suggests we start at 1, 1, 1. It doesn't matter that much. It's going to find the right answer for most starting points. There are a few places where you could start it that it would get stuck, but and we see our values have changed a little bit. So our slope has changed to 0.7 and our intercept has changed to 1.58. So that was the concession that was made to get m squared plus b squared down to 3 while still trying to fit the points as well as possible. All right, so we also want to review a little bit of Taylor series. And the key idea of Taylor series is that functions might be quite complicated, but polynomials are much simpler, especially linear and quadratic polynomials. It's much easier to reason about how they behave. And if you zoom in around a point, most functions do sort of look linear or quadratic. So the quadratic approximation is going to fit the graph a little bit better than the linear approximation. And if you want to use a cubic term as well, that's going to fit it even better. So here we have a quadratic term hugging the graph of this function f of x. And you can see that at the base point 0. And you can see that it's doing quite a nice job of hugging the graph. So the second order Taylor polynomial of a function around a base point a starts at the value of the function at a. So that's kind of setting the initial value correctly. And then as you move away from a little bit, so that's represented by x minus a. That's the vector indicating how far you've moved away from a and in which direction. If you dot that displacement vector with the gradient of the function at that base point, then that gives you the linear behavior of the function. And then if you take that displacement vector x minus a and multiply it on the left and on the right by what's called the Hessian, the second derivative, the matrix of second derivatives, then that gives you the quadratic behavior of the function. So let's look at an example with single variable. So we have this function e to the x minus 2x, and here's its graph over the interval from 0 to 1, and you can see it has a minimum right there. And we can identify where that minimum is by differentiating the function. If we differentiate e to the x minus 2x, we get e to the x minus 2. If we set that equal to 0 to find where this function is going flat, we find that x is equal to log of 2. So that's going to be that value. And what we want to do is Taylor expand around that point in order to get the behavior of the original blue function, e to the x minus 2x, to get it approximated using a quadratic as well as possible. So the linear approximation is just flat. The gradient, or in other words, the derivative is 0 there. So the line is going to be flat. To get the quadratic term, so we start at the correct value, 2 minus 2 log 2. Then we need to add some quadratic stuff. So it's going to be squaring how far we are from that base point. But then we need to match up. Actually, let's just run this and see what it looks like. So actually that does a decent job. So maybe 1 is the correct value here. If you use an incorrect value, then you'll see that it doesn't match up with the blue curve as well. So we need to figure out what value goes here. And to do that, we differentiate the function f twice and then plug in the base point. And when we differentiate twice, we get e to the x, and then we plug in the base point of log 2 and we get 2. So 2 goes here. But then also there's a factor of a half because when you look at the Taylor series, the quadratic term has an extra factor of a half out front. So we were right in the first place. There's a 1 that goes there. And that green function is going to be the quadratic function that approximates the blue one as well as possible. Let's see what happens when it's a little too small. If we multiply by a half again, then you can see the green one sort of misses the blue one on the other side. So moving up from 1 dimension to 2 dimensions, we get some more interesting behavior. So you can have, of course, a bowl shape like this. That's very much analogous to the parabola, upturned parabola type shape here. You can also get saddle behavior where the function is upturned in one direction and downturned in the other direction. So for example here, looks like a saddle or like a Pringle chip or something. You have an upward slope in this direction and then a downward slope coming back the other way. And so you have neither a maximum nor a minimum here. So this question of determining whether you have a saddle point, and also if you have a bowl shape, whether it's something that's really more like a bowl like this, or something that's more valley shaped, like what we saw above, you really want to be able to detect that behavior. It's going to end up being pretty important for optimization in higher dimensions, because different optimization algorithms are going to have different behavior depending on whether the local minimum that they're trying to converge to is something like this versus something more like the bowl shape, like that. So the key idea for determining that behavior is to use the spectral theorem. So the idea is, let's take the Hessian and expand it according to its eigendecomposition. We know that exists because the Hessian is going to be a symmetric matrix. And so not only does the eigendecomposition exist, but the vectors are going to be orthonormal. So we can write the Hessian out as lambda 1 times u1 transpose, where u1 is the first eigenvector and lambda 1 is the first eigenvalue, and so on, adding up terms for all the eigenvectors until we get to the last one. And then we, instead of thinking about this displacement vector x minus a, which is telling us how we're moving away from that base point, instead of thinking of it in the original basis, the standard basis that it's given in, we think of it in terms of the basis of eigenvectors, u1 up to un. So we write it out as c1, u1, and so on up to cn, un. So these c's are just telling us how much we're going in that direction specified by that particular eigenvector. So if we do that, we just take this expression and we multiply it on the right, and we transpose it and multiply it on the left by the Hessian. We get kind of a big expression, but every term involves u's, and when u's multiply each other, they're going to give zeros most of the time because they're orthogonal to one another. And the only time they don't is if you have a vector hitting itself, and then it gives 1. So things simplify quite a bit. Let's maybe take a look at that. When we multiply out this part, what's going to happen is that we're going to get this term from this product, and this term from this product, and similarly for all the ones in between, and then all of the cross terms are going to be 0. Anytime you have ui prime times uj, where I and j are different, these are all going to be 0. And then similarly, when we distribute here between these two factors, and we end up with this expression. And this formula makes it really easy to think about what's going on, because if we assume that we've ordered the lambdas so that lambda 1 is the biggest and lambda n is the smallest, then what's happening is that as we move in the u1 direction, the function looks like a parabola with a coefficient of 1/2 lambda 1. And that means it's going to be as steep as possible. That's going to be the direction where we have the sort of steepest canyon walls. And here, if we move in the direction of the last eigenvector, then it's going to be as shallow as possible. That's going to be the direction that's most like moving along the bottom of a valley. So we can tell by the relative sizes of lambda 1 and lambda n how extreme this difference is between the directions where we have the greatest curvature and the directions where we have the least curvature. So for example, with the problem that we started with, we might look at the Hessian and check its eigenvalues. And we get these radical expressions. So that's SimPy exactly finding the eigenvalues for us. But if we want to compare how big they are, we'd rather just see decimal representations. And sure enough, one of them is over 200 and the other one is less than 4. So there's one direction, namely the direction of the eigenvector corresponding to this larger eigenvalue, where the walls are really steep, and then the orthogonal direction where it's much more shallow. So that corresponds to the bottom of that valley. If we want, we can go back to the original question and see the direction of the valley by plotting the eigenvectors of the Hessian. And what we see is that this green line segment does go straight along the bottom, and then this pink one indicating the direction of the other eigenvector is the direction where the walls are steepest.